Section 13.4, we're going to look at tessellations of the plane. So to start with, let's actually define what a tessellation is. A tessellation of the plane is a way to fill the plane with copies of congruent figures so that there are no overlaps and no gaps. And like I said, that's to some degree what you guys were doing up here. I didn't see anybody do any overlaps in any of your pictures that you did up front. Some of you had gaps depending on what you were trying to create. But there were places where all of you did activities where you did try to fill in gaps. And that's the idea of tessellation, is filling in the gaps. Now, you didn't always do it with congruent figures. So that meant that some of the things that you created up here weren't necessarily tessellations. Now, in Jay's group, you guys created a pineapple. Do you remember that one? That would have been a tessellation, right? At least the yellow part. Because it was all yellow tile pieces were congruent to each other. They were all pieced together, and there were no gaps or overlaps. These are some very boring tessellations, the first two, because they're just grids. One looks like bricks, right? Very, very boring. But they fit the description. There's no gaps, there's no overlaps, and they are congruent figures. The first one's a square. The second one might be square or rectangle, kind of hard to tell, but we've got something that's a pretty basic shape. A regular tessellation is a tessellation that's done with regular polygons. Okay, so now this is like quiz time, not really, but does anybody remember what the word regular means when we're talking about polygons?
All the sides and angles.
All right, so we've got all congruent sides, all congruent angles. And of course, not every shape will tessellate when they do that. Some will, some won't. The first picture up here where it was squares, that would be a regular polygon. 4 congruent sides, 4 congruent angles. Down here on the bottom left-hand corner, there's triangles. Specifically, what kind of triangles would you suspect they're trying to say these are? Equilateral. 3 congruent angles, 3 congruent sides. And then the one on the right-hand side looks like a hexagon. The yellow shapes that both groups were working on at the front, right? Okay, so 6 congruent sides, 6 congruent angles. Not all regular polygons will tessellate. The sum at every vertex, when they actually fill it in without any gaps or overlaps, has to be 360. So what that means is that the number of angles at each vertex would have to be 360 divided by the angle measure. Thus, the angle measure for the polygons must evenly divide 360. So let's talk about a square. What are the angle measures in a square? 90 degrees. Does 90 evenly divide 360? Yes, and that's what means it's going to tessellate. How about an equilateral triangle? 60 degrees. Does 60 evenly divide 360? It does, so that's why the triangle, an equilateral triangle, will tessellate. Let's try it with 5. Does anyone remember the angle measure for a pentagon? I don't remember now. I was thinking 72.
Oh yeah, 7.
Is that right? No, that's not right either. I don't have it written down. This is what happens when you just do this on the spot, right? So how do we find it? Let's do that. Let's do it. Let's find it all together. What do you do? That would be the interior angles. I want to do the exterior angles. That's what we're looking for, the angles of the polygon. Do you remember, Alyssa?
I remember you subtract 2 somewhere in there.
Mm-hmm. You take the number of sides minus 2, and you multiply it by 180. And because 180, because we split it into triangles. Some of the triangles, 180, yeah. And do you remember what you divide by? The number of sides, n. So let's try this for 5, a pentagon. So you do 5 minus 2, that would be 3 times 180 divided by 5. What do you get? 108. 108 is the number. So this magic number for a pentagon is 108. So take your calculator. I want you to try 360 divided by 108. 360 divided by 108. Yeah, it doesn't work, does it? Okay, and actually that's what we're going to do on this example. It asks us which regular polygons will tessellate a plane. Now we've done a few of them already. So we did equilateral triangle. So the equilateral triangle has 60-degree angles, and we know that 360 divided by 60 equals what? I'm sorry, 360 divided by 3, because there's three angle measures. Okay, that's loud. This is 120, right? Okay, it evenly divides. Let's do a square. So if we did 360 divided by 4, will that divide evenly? Yeah, 90. Notice I'm dividing by the side measures because it's easier than dividing by the angle measures, and they interchange, so that's okay. We tried a pentagon in a moment ago, so let's just see what happens with the pentagon. So a pentagon, we don't have it written down, but you and I both discovered a minute ago that it's 108 degrees, right? What happens if you divide 360 by 5? You get 72. Is that the 108 that we were supposed to get for the angle measures for the pentagon? No, it doesn't work like that. Let's go up to hexagon and then we'll pause. In a hexagon, how many sides do we have? You have 6. Does 360 divide by 6 evenly? It does. It would give me a 60-degree angle. Now, what I want you to notice when we're doing this one right here is that if you were to take a hexagon, it would be 4 times 180 divided by 6. So what is 4 times 180 divided by 6? What do you get? 120. So could you take the 360 degrees and divide it by 120 and get it to go in evenly? Yeah, you can. It's 3 times. And in fact, if you take a look at, maybe I should have drawn these and written these a little bit differently. Let me just mark them out and do it the other direction because I think it might be easier to see. Let's do the 360 divided by 60, which gives me what? 6, right? This would be, yeah, because I want to make a connection later too. 360 divided by 90 gives me 4. This one was trying to be 360 divided by 108, and that one didn't work, right? And then this was 360 divided by 120 is 3. Okay, so take a look at this. You cannot see that purple at all. You can do a different color. This divides evenly to give me 6, divides evenly to give me 4, divides evenly to give me 3. Okay? In order for it to divide evenly, it's got to give me an integer number when I'm done, right? Can I divide this evenly and get a 5 when I'm done? Well, I mean, I can divide it by 72. Obviously, I tried something akin to that right here, right? 360 divided by 5 gave me 72, so 360 divided by 72 would give me 5. But there is no regular polygon that has angle measure 72, so it doesn't work. The other thing to notice is that they're decreasing. So this is 6, 4, this is 3. What would come next? If we're decreasing in the answer that we're getting. We tried, I mean, 6 was there, 5 didn't work, 4 is there, 3 is there. What's next? 2. What would I have to divide by to get a 2? 180. Can you have an angle measure in a polygon that's 180? No. I mean, it's a side then, right? It's actually a side. So I'm done. There aren't any more polygons that work. These 3 are the only ones that work: an equilateral triangle, a square, and a hexagon. They are the only 3 regular polygons that tessellate. Now, they're not the only polygons that tessellate. They're the only regular polygons that tessellate. So let's actually see something else that will be not regular that will tessellate. So we're going to look at tessellating with other shapes. Non-regular polygons can be used in tessellations too. For any convex quadrilateral, half turns of a quadrilateral around the midpoint of its side produces shapes that fit together at a common vertex and can be used for a tessellation. So the figure on the right is the original, the one that's drawn with black. And what they've done is they've taken the midpoint, let's look at S, of the side. Okay? And then they've rotated this shape 180 degrees down here. So this is a rotate, the figure underneath it is a rotation 180 degrees. And they've done the same thing over point P. They've rotated 180 degrees. This is their rotation figure. And if you can imagine this point Q being over here, because it would be reflected down and they rotate it, it would be over here. Okay? So all 4 of these actually do create the tessellation because these are congruent shapes. It's not a regular shape, but it is congruent. So for instance, if you're taking a look, say, at angle C, you see angle C here, correct? And if you're looking at, say, angle B, you see angle B here. And if you're looking at angle D, you see angle D here. And then the angle A didn't change. So the point that I'm trying to make is that these 4 angles that are all meeting at the point were the same 4 angles that were in the quadrilateral to begin with. So if they were in the quadrilateral to begin with and it's a quadrilateral, then they have to add up to 360 because it's quadrilateral. So that's why when they're meeting all at that point and put together in the right way, they add up to 360 again. Because they already had that property. We just rotated things around to get them to show up. So this is one way to create a tessellation with non-regular shapes. There's a couple others we're going to look at. Another way to create a tessellation of a plane is to take a polygon that tessellates like a square or a triangle or a hexagon and then manipulate one side. So we're going to cut out a design on one side of the polygon, slide that design to the other side of the polygon, and then the shapes fit together. So you can see at the top here they've got this design they've cut out, and then they've mirrored that across to the bottom of it, right? And each one of these figures is identical to the other one in terms of its shape. They're manipulations of the square, but the top edge, you know, the curve that it now is, mirrors the bottom curve. Okay, it's a perfect image. And they all have that. Now, not only can you do that on one side, you could do it on 2 sides, right? If I can manipulate the top and the bottom to be this mirror image that's not quite a straight line, you could do it on the left and the right, and it would be even more creative. Agreed? You could do something funny shaped over here on the left, and then it would mirror to the right, and it would all reflect across, not reflect, but it would shift across or slide across to the other side of the image. So this is one way, or second way, to do tessellations that are non-regular. There is a third way. A third way to tessellate a plane with a non-regular shape is to cut along half of the side of an equilateral triangle and then rotate the shape 180 degrees clockwise to the other half of the side. And this can be done, wouldn't have to be, but could be done on all 3 sides. So you'll see this is the cutout, right? It's blue, and then it's cut over here. And then they've rotated this around here. So it's indented from B to C or B to O, and it's sort of outdented is not a word, but you know what I mean, right? It's outdented over here from O to C. Same image, but it's outdented. Yeah, okay? And then you could do it, like it said, to all 3 sides. So you could do this here. You could create some other shape between A and B. You could create yet another shape between A and C. You just have to create the midpoint and create the image with the rotation. And then you get an image that would look something maybe like this. So there's one more slide, and then we're going to talk about what all this means. Your book also shows other details on how to create more intricate tessellations using rectangles or squares. And I'd like for you to think about this as mathematical art in your classroom. Now, for those of you who've been in my office, which is most of you at this point, I have mathematical art on my office. I don't have tessellations. I probably should. That would be pretty cool. I have fractals mostly on my walls. But mathematical art is cool stuff. So this one right here is an example of mathematical art with tessellations. They look like what? They look like fish. This is a tessellation by a gentleman named M.C. Escher. He does some really cool stuff. If you Google M.C. Escher, you'll find some really cool things. There is a fair warning at the bottom of the slide. M.C. Escher is a very dark artist. He does some really kind of creepy things. So there's some of his things that you probably are going to be like, you're not going to be freaked out about, but they're probably not appropriate for, a third grade classroom, okay? They're just not. You're going to be like, okay, that's really weird looking. But he does have some cool things that are just fine. Obviously, the fish here would be one of those things. Yes?
So my grandma, she quilts and stuff, and she has this little game, I guess you could say, and it's a plastic rectangle, and there's all these different shapes, pentagons, triangles, random stuff, and they only fit in the rectangle one way, and you have to put them all in until they all completely fit with no gaps in the whole thing. I got it one time because she took a little picture of me with it because I try it all the time, but it's like this, and you have to fit them all in with no gaps into this shape.
Yeah, so you've got some homework questions on there, but you'll notice there's not very many. Do you guys see that? The homework in this section is very brief. Any idea why that might be? You're going to create one of these. Yes. You know what? I'm going to keep recording this. That way, just in case you want to listen to the instructions again, you can. It'll be at the end of this video. You're going to create a tessellation for your exam. It will be due at the time you have your exam. So that means you've got 9 days to create this tessellation. My suggestion to you would be to create and to think through and to come ask me questions about it before I leave on Friday. And here's why. You don't get to redo this on your test. So if you botch this part of it up, this is just it. You have opportunity before the test because I'm telling you this is what it is. Okay? So let me just read you the instructions that are on the test, and I'll bring you the actual copy of these instructions next time as well. Here you go. I want to just totally pull these all out. You are to bring with you, I'm going to show you some examples too from classmates of yours in the past, so to speak. You are to bring with you create a tessellation of the plane to your exam. This tessellation should be at least 10 copies of the same figure. Fit it together with one of the tessellating polygons we've discussed in class. Your image should not simply be a polygon. For example, if you just drew me squares and drew them as bricks, you're not going to get a good grade. It's not going to work, okay? Your image should be precise. It should have some changes made in artistic detail. It should have color. It should be interesting. It should, for lack of better terms, look like something. This looks like fish. If you look back at this one over here, with given a little bit more artistic detail, you might look at this and say it's some kind of a mountain range. This was not very exciting, but some kind of an image is going on. If you've created this one over here, there's not a lot here right now. It's just the colors, but there needs to be something created in it where you look at it and you see something going on. I'm going to show you examples, so you're going to be like, I know what she's talking about now. So bear with me. You'll see some examples.
Can you differentiate it with the different colors you use?
Yes, you can. Yes, you can. I'll show you. This will be worth 12 points on your exam. And you can come talk to me about it beforehand, and I can tell you what you're doing wrong. So I strongly advise you to take that opportunity. Come chat with me and say, did I hit it? Do I have what you're looking for? Okay? You're going to do this on a plain white sheet of, paper. Start with, do not give me lined something. So plain white sheet of paper like this, okay? And you're going to put this in with your exam when you turn your exam in. What else did I say? Yep, you can't redo it. Come see me beforehand. Your work will be graded on the following criterion. Again, I'll bring you this part next time. I didn't make copies yet. Needs to be precise. Okay, so if it's supposed to be a straight line edge, you probably should be using a ruler to draw it straight. It's not a freehand activity. Now, the parts where you do curved features aren't going to be able to have that ruler potentially with them, but they should be precise. It should look clean. If I were to take your shape that you're saying you're tessellating, I should be able to put it on top of all your shapes and they match. Okay? It should be neat. It should be clean. It should be colorful. And it should be identifiable. Okay, so let me show you some pictures and then you'll have an idea.